Power. Power is how much work is done per second. Power is the work done per unit time. Or it can also be said as the rate of work. Work is a change in energy, so that's measured in joules. Time for this should be in seconds. And so we get a new unit for power, which we call watts. The watt is named after the Watt that invented the steam engine, James Watt, but I'm not sure. Anyways, so that's 1 joule per second or 1 watt. Now remember that a joule is equal to a Newton meter. So we're at Newton meters per second. And a Newton is equal to a kilogram meter per second squared. So that's times a meter divided by seconds. So a watt can be reduced to fundamental units of kilogram meter squared per second cubed. So that's what power is. Now to understand this, we can think of some specific kinds of devices. The first thing I want to think about is devices that have a pi power but don't use a lot of energy. So I think of two basic devices when I'm doing this. Well, there's lots, but the two that come to mind immediately are the flash on your camera or a toaster. The flash on your camera produces a lot of light in a small amount of time, so it uses a lot of the energy of your battery in your camera in a split second. That's a very high power device, a lot of energy per unit time. A toaster doesn't stay on very long, so it doesn't use a ton of energy. It doesn't accumulate a lot of stuff used, but when it heats up your bread very quickly, making it toast in that small region, it heats up very fast and uses a lot of power, a lot of electrical energy in that short period of time. Some devices, on the other hand, have very low power. I think of something like a cell phone or an iPod or these modern electrical devices that run on these batteries. Because it's critical for them to last a long period of time, they're very carefully designed to not use very much energy per unit time. A lot of the reason why your iPod can last for a very long period of time on one battery is not because the battery itself is great, although the battery technology has come a long way and it's very good. But it's really because the circuitry in an iPod has been very cleverly designed to use as little power as possible by shutting off systems when you're not using them, like the backlight on your iPod doesn't stay on when you're not looking at it, and by running as efficiently as possible to produce as little or to use as little energy per second as possible. There are, of course, devices that use a lot of power and are on all the time. Something, for example, like your dryer uses a lot of energy and has to run for a long cycle, and as a result, it's not great. It does use a lot of energy. Energy, then, we can think about is the total amount that gets done. It's the accumulation. When we think of your electrical bill for your house, you don't pay for the power you used in a month. You pay for the energy that you used in a month. It's not a matter of what the most electricity used in an individual second it was in your house, but it's about how much you accumulated over the entire month. So energy is an accumulation, where power we can think of as an instantaneous use of energy. So let's do a really simple problem here where we're going to look at how much power you're going to generate when you lift 10 books from the floor onto a table that's 1.5 meters off the floor. So there's a whole bunch of books down here. And you have a table. And the table is 1.5 meters high. So it's pretty high. And here you are. And you're going to take the 1 kilogram books, you're going to pick them up off the floor, and you're going to put them up on the table. So the work you're doing here can be measured as the change in energy of these books, who start on the floor at rest and end up on the table at rest. So the change in energy that occurs here is gravitational potential energy. So the work done is going to be the gravitational potential energy that you give these books. There's 10 of them at 1 kilogram each, so that's 10 kilograms of book. We're going to assume that you're lifting these books near the surface of the earth, and you're raising them up by a total of 1.5 meters. So the work that you're going to do is 147 joules of work. Now, how much power do you have while doing that? Well, power is equal to the amount of work you do per unit time. So you did 147 joules of work, and you did it in 34 seconds. So that means that you did 4.3 watts of work, or joules per second of work. So again, power is how much energy per unit second, or per unit time. It's an instantaneous, and it's a measure of what the device is doing at that second. Energy is how much power accumulates over time. So if we have something where we can look at the amount of energy that is changed, or the work being done, and we can divide it by the amount of time, we can figure out how much power, this would be average, was exerted while the work was being done.